All right, welcome back. We are at lecture 3B for differential equations in linear algebra. I say welcoming back. This is a different video. You should watch video 3A. I'll put a link to that in the upper right corner here. This is the linear algebra portion of lecture 3, lecture 3B. Let's start by reviewing the end of lecture 2. Graphing a linear equation in rectangular coordinates, also called Cartesian coordinates, and skew coordinates. The less official name for that is slanted coordinates. And it's going to be the same example from the end of lecture 2. We're going to look at essentially the same linear equation, 4 times the first coordinate plus 5 times the second coordinate equals the constant 10 in both cases. But they're going to produce different graphs based on the two different coordinate systems. Here's something important though, subtle things to keep track of. You want to imagine both coordinate systems as being the same plane with the same points. And even the origin is going to be at the same spot in both. They're going to be two separate pictures, but you want to imagine them being on the same plane, and imposed on the same plane with the same location for the origin. That's going to be really important to understand what's going on. So here is the graph in rectangular coordinates, Cartesian coordinates. Plot points, to help you plot points, you can solve for y as a function of x. Subtract 4x from both sides, divide both sides by 5. You get 10 minus 4x over 5, which is 2 minus 4/5 x. You can then make a table of values. To help you plot, you could pick different things for the independent variable, like what I picked here, -3, -2, -1, 0, 1, 2, 3. Plug those in for x to get y. Let me just do one of them. If I plug in x equals 2, for example, I'm going to get 2 minus 4/5 times 2 is 8/5. It's going to be a 10/5 minus 8/5, which is going to be a 2/5. That's a 5 there, which is 0.4. 2/5, which is 0.4, and you plot the point with rectangular coordinates 2, 0.4. That's this point right there. 2, 0.4 are its coordinates. Okay, something you've done hopefully since about 8th grade or so. But don't leave the video. There's so many subtle things here that are hard for people, including people taking differential equations in linear algebra, that you want to pay attention to. What about the skew coordinate system? So I'm about to show you another picture over here that you want to, again, pretend is the same plane, and the origin is at the same spot, and in fact the vertical axis is at the same spot with the same scale even. Looks like this. It's called a skew coordinate system. One axis is slanted. Use different letters for clarity here, but again, pretend it's the same plane, same corresponding points, same origin, same vertical axis, location and distances are still 1 unit apart. This is the graph of 4u plus 5v equals 10. Really the same equation, essentially the same equation. 4 times the first coordinate plus 5 times the second coordinate equals 10. But the graph is different. These are two different lines. As sets of points in these same planes, there are different sets of points, except for one shared point at right here. This point right there is the same point, same spot as this point over here. 0, 2, and in fact it has coordinates 0, 2 in both cases. Essentially, to plot it, you do the same kind of thing you did before. Solve for v as a function of u. You'll get v is 2 minus 4/5 u. And you'd make a similar table, except go ahead and call this u and this v. And then when you plot points, like the point with coordinates 2.4, you've got to plot them with respect to this coordinate system. That's this point right there. Go 2 units along the u-axis and 0.4 units along the v-axis. Make that a slanted line and this a vertical line. Got to make those parallel to the axes. That is the point whose u-v coordinates are 2.4. It's a different point than this point right there. Again, imagining these planes are the same plane with the origins in the same spot. Same kind of equation, but a different graph because the coordinate system is different. In a little bit, I'm going to show you that you can also do something else. You can take either of these graphs, say this one, based on rectangular coordinates, and convert the same line to UV coordinates based on that coordinate system. Its equation will be different in that case, though, in terms of U and V. The same equation, essentially, in this case, produces different graphs. But with a given graph, if I go to a new coordinate system and find the equivalent equation in terms of U and V, it'll be a fundamentally different equation. It'll still be linear. We'll come back to that. Let's get into some details before we do that, though. We want to transform between the coordinate systems via what's called a linear transformation. All right, given a point P in the plane, sometimes mathematicians say the plane, but you might be saying, aren't there many planes? Well, okay, the plane is just shorthand for the plane we're working with. And it's rectangular Cartesian coordinates, x, y. Question, can we find its skew coordinates? And now I'm talking about the same point in both pictures, the same location, because they're the same plane. Can we find its UV coordinates, its skew coordinates? Yes. And you can do it by a linear transformation, a linear change of variables. I'm going to tell you what the answer is. It's not going to be clear how I got this, though you could spend some time investigating if you want. Later on, we'll talk about how to come up with these equations. This system of equations for U and V as functions of x and y. You want to think of this system of equations as a pair, in a sense, to give you a single transformation that converts x, y coordinates for a given point to corresponding UV coordinates. For example, considering our point 2, point 4, on the left picture, if I change the axes and made them UV axes, like in the right picture, what would the new coordinates point of that point be in U and V? Plug into these equations. U would be square root of 2 times x, square root of 2 times 2. And V would be negative x plus y. Negative 2 plus 0.4 is negative 1.6. About this. Does that make sense? Let's go back and see if we can make sense out of that. Remember that those coordinates, 2.8 comma negative 1.6. 2.8 comma negative 1.6. We're talking about this point right there. Try to imagine the corresponding point over here. I'm going to try to stay level, same height here as I go over here, and the same distance from the vertical axis approximately is not going to be the same as this actually. It'll be a little further, I think. Something like around here. Remember what the skew coordinates were? I think it was about 2.8. 2.8 units along the u-axis, and then go down. And V was about, I forgot, negative 1.2 was it? I forgot. Negative 1.6. So it really should be a little lower. It's really more like right about there is the corresponding point. Here's the origin, matching that origin over there. This is a little bit above the origin from a horizontal line through the origin. Right about there is our point. Its UV coordinates are, again, approximately 2.8, negative 1.6. And you can check other ones. Can we reverse the process? Given UV coordinates, can we find the x, y coordinates? Sure. Just solve this system of equations for x and y in terms of u and v. The first equation is easy to do. Divide both sides by square root of 2. X would be 1 over square root of 2 times u. Take this one. Add x to both sides. You get y is x plus v, but x is 1 over square root of 2 times u. It's this system of equations that converts from u to v in terms of back to xy. There we go. It's not always so easy to solve. This was easier because I could quickly solve for x in terms of u, but sometimes it'll be more complicated. So you could try this. You could take this uv coordinates at the same point and plug into there to get these coordinates. Try it. 1 over square root of 2 times u is the 1 over square root of 2 times this. Square root of 2's cancel, leaving you with 2. Matches the 2 there. Then plug this in here for u and negative 1.6 in for v. Again, the square root of 2's will cancel. You'll get 2 minus 1.6 is 0.4. Okay, so it does work. And you should probably take the time to check that with other points. Not telling you where I got these equations. You're just trusting me here. These systems of equations going either way are called linear transformations. Linear transformations, that's going to be a key word for us, especially in Chapter 1 of Visual Linear Algebra Online, and we use it in later chapters. And that means they're really linear functions. The word transformation is essentially the equivalent to function, though we often imagine them more geometrically. If they're functions, they've got domain and codomain. Domain is the set of all inputs. Codomain is sometimes called the target, is the kinds of outputs that you get. In this case, both the inputs and the outputs are two-dimensional points, two-dimensional plane. The points themselves are, of course, zero-dimensional, but they're sitting inside a two-dimensional plane. We denote two-dimensional space by these symbols. Oh, they didn't show up. Remember the dot, dot, dots didn't work. Okay, that's unfortunate. Very pretty symbols. What I meant to be there is an R2, and this R is supposed to be kind of a fancy R. It's called a double struck R. You put 2 lines there. R2 is shorthand for two-dimensional space. The 2 represents two-dimensional. The R represents the fact that its coordinates, no matter which coordinate system you use, are real numbers. This is also written as R cross R. You don't say R times R, you say R cross R. That's called the Cartesian product. And when you write that, it's essentially emphasizing that the elements can be thought of or represented as ordered pairs. In this case, where the first entry of the ordered pair is a real number and the second one as well. Cartesian product, you can look that up. We also use the following kind of notations. Function notation. More trouble with going from a Mac to a PC. These lines should be connected here. UV equals t of xy. T is the function name. Equals this. And for the inverse function, I could write a t inverse. Notice the negative 1 up there. That's not a number. That's not t to the negative 1 power. It's the inverse function of t. You know about inverse functions. To go take an input uv and give you back xy. These are the same as the systems of equations on the previous slide. Now we are writing the inputs and outputs as two-dimensional vectors. These columns of numbers as two-dimensional vectors. Do we have to write them in this way? No, we could write them as points. I could have written uv as a point equals t of xy as a point equals square root of 2x comma negative x plus y. I could have written it that way. It would have been okay. But there's good reasons for us in this class to write them as columns when we are plugging them into linear transformations, or ultimately later on when we multiply them by matrices. We could call these vectors. And we could also write this kind of thing. Hey, there the R showed up, so I don't know what the difference was. So here's the fancy looking R. It's even fancier than when you read it by hand. You'll see these kind of notations. I'll use this in this class. This emphasizes t is a function whose domain is R2, two-dimensional plane, and whose codomain, whose target is R2. The inputs are all of R2, all the points in the plane, and the outputs are two-dimensional points in the plane, not necessarily all of them, because it might not be an onto function, but in this case, it will be onto. And the inverse function is a similar kind of thing, two-dimensional inputs, two-dimensional outputs. We will consider situations where the dimensions of the inputs and outputs are not the same. You might have an R3 there and an R4 there, three-dimensional space and four-dimensional space. That doesn't have to be the same in general. This is common notation to use, so it's something you want to get used to. This is my introduction to it. Remember I mentioned a few minutes ago that the graphs themselves can be converted to new coordinates and still be the same set of points. For example, this equation 4x plus 5y equals 10 can get transformed upon substitution to an equation involving u and v in skew coordinates that will represent the same set of points in that same plane. But the equation will be different. Use those transformations. What was x? Was it square root of 2 times u? Oh, no, it was 1 over square root of 2 times u. Yeah, there's x. That's x. There's y. I'm replacing x and y with what they equal in terms of u and v. And then I can simplify that. I can distribute this through and this through. I'm really going to get a 4 plus 5 is 9 over square root of 2 times u, and a 5 times v equals 10. That's fine as an equation in terms of u and v. You may want to rearrange, you might want to multiply everything by square root of 2, and you may want to solve for v as a function of u, and that's some things I did there, and I approximated as well. This will help us here in a second to see that it's the same graph. Remember that, v is approximately, let's write it up here. V is approximately negative 1.3 u plus 2. Let's go back to the picture. Way back, a ways ago. This line right there is a set of points in uv coordinates. The y-axis is the same as the v-axis. The u-axis is going to go like this. This equation, vertical intercept of 2, it's the same set of points. Slope, negative 1.3. Rate of change of v with respect to u is negative 1.3. Which it's not obvious that that's the case here. Because I don't have that around there. Actually, I'm thinking maybe it's looking wrong even. But I don't want to stop the video. I need to double check this. Because I'm thinking u equals one unit of distance is about like that there. I need to double check this. So there could be a mistake here. Before, in lecture 4b, we'll probably look at this again, and I'll just be double checking that things are right. But ultimately, it's supposed to be the same set of points, but now with respect to u and v. And I can do the same kind of thing. I can go with the other graph in terms of u and v and transform it to get in terms of x and y and be the same set of points. Go ahead and replace u with square root of 2 times x, replace v with negative x plus y, simplify, rearrange, get approximate that. Okay, so I think in lecture 4b I will try to confirm that this really does seem right. Hopefully I haven't made a mistake. Again, I do make mistakes, so there could be a mistake here. I'll get back to you about it. Okay, maybe you want to think about it on your own. It's the same geometric set of points. All right, here's the last few slides. What exactly are vectors? I got to go kind of quick. Well, maybe I got 15 minutes or so here. What exactly are vectors? I sort of mentioned that you can think of the columns as vectors, as points, which can be thought of as vectors. Is that what a vector is? Well, sometimes vectors can be thought of as columns of numbers. That will be the way we mostly think about them, actually, when we're doing calculations, at least. But in physics, or engineering, you probably were taught, maybe even back in high school, that vectors are arrows directed quantities that are typically imagined and drawn in two-dimensional or three-dimensional space, things like this. It's an arrow. It's a two-dimensional vector sitting in the plane. This one, if you imagine this perspective, is a three-dimensional vector sitting in three-dimensional space. Maybe it, well, this kind of comes out of the screen based on the way this box is situated. Imagine it's three-dimensional. They can represent quantities like, these are the most common quantities, position. Where are you with respect to some origin, for example? An arrow drawn from the origin to your location would be your position vector. Displacement, which is change of position, say for a motion, maybe a bug is flying around, starts right here and flies around and ends up over here after moving up and down a lot. An arrow from this point to that point would be a displacement vector, a change in position. A velocity vector, bug's flying around at any moment in time. You imagine the bug is at a certain point and it's got a certain direction of motion, tangent to the curve, and a certain speed. The speed is the length of the velocity vector. But is it a vector because there's a certain direction to it? This even works with one-dimensional motion, up-down motion, say. The positive direction's this direction. Upward motion you'd want to think of as a positive velocity. Downward motion you want to think of as a negative velocity. Acceleration, or momentum, acceleration and force. Forces have a strength to them, a length to their vectors, and a direction to them. That's the direction of the force. There's also plenty of other things that can represent. For a given vector, this is a big thing that's emphasized. It doesn't matter where you put its tail. The bottom or starting point of the vector is the tail. As a starting point. And the tip of the arrow is called the head. You can think of it as a point as well. I mean, you could call the whole arrow part itself the head, but it's better to think of it as a point at the tip. And it doesn't matter where you put the vector as far as what vector it is. All that matters is that it's got the right length and direction. These two arrows are thought of as the same vector, even though their tails, their initial points or base points are in different spots. Can you do a rigid translation to get one to the other? They have the same length and the same direction. They are the same vector. Where you put the vector, where you put its tail, is helpful to put in different spots depending on what the application is. So like for a displacement vector from here to here, it's good to put the tail at the starting point for the bug and the head at the ending point. Don't put it somewhere else. It makes more sense to put it in the actual locations. For the velocity vector, it's good to put the tail at the spot the bug is at that moment in time, pointing in the direction of motion. It changes over time because the bug's speed and direction change as it flies. Okay? You don't want to put the vector somewhere else. It wouldn't make intuitive sense, even though you theoretically could. What exactly are vectors? Continued. There's also something called the zero vector, which has length direct 0 and no direction, and we draw it as a point. There it is. See that? That's not a typo there. That red dot is supposed to be there. So a dot as a vector is the zero vector. Why would we call it the zero vector? I mean, it makes some sense. It's based on the algebra of vectors. It acts as what's called an additive identity. When I add the zero vector to any other vector, I get that other vector back. Which begs the question, how do you add vectors? That's coming to here in a minute. Vectors can be resolved into what I call their components. Visually, we can imagine it this way. So this blue vector points to the southwest, you might say, or west-southwest. it's got a horizontal component of -3 because it's pointing to the left. You want to think of leftward as negative, rightward as positive, typically. At least you want to imagine that. And it's got a vertical component of -1 because it's pointing downward. By the way, I say component, some people say component. Okay, I hope you're okay if I say component, but your other teachers say component. So that's the components of the blue. The red has horizontal component +2 and vertical component 1. Notice these are right triangles. I'm really thinking of these in terms of the rectangular coordinate system when I say these are the components, not a skew coordinate system, though I could write them in terms of skew coordinates. This one's pointing to the northwest. Its first component, its horizontal component is -1, its vertical is +4. This one's pointing to the southeast, horizontal component of 2, vertical component of -2. Or, again, first component of 2, second component of -2. Could I call those coordinates as well? Yeah. When you're talking arrows, though, it's better to call them components if you want to be consistent with other people. There's also a natural association between points in a rectangular coordinate system and their position vectors. I got a point here, make it blue, and that's a single point. Got a coordinate system, rectangular coordinates. What's its position vector? It's always with respect to the origin. The origin's right there. Draw an arrow starting at the origin, ending at this point. That's its natural associated position vector. Likewise, if I got a vector drawn at an arbitrary location, I can translate it without rotating it, or without stretching it, a rigid translation, so that its tail is at the origin, and pretend this has got the same length and same direction. It would correspond to this point right there. Natural association between points in a rectangular coordinate system and vectors, position vectors, they're called. And you want to have the freedom to sometimes think of vectors as being points and sometimes think of them as being arrows. That'll be really important. So many subtleties that are really important if you really want to get this. In addition, this association can be generalized to an association between points and their position vectors described with respect to other coordinate systems like skew coordinates. But we won't get into that now, not for quite a while here. Representing vectors. When typing, we commonly use a bold-faced letter like this to represent a vector quantity. Are vectors numbers? No, they're not numbers. Are they quantities? Yeah, they can be thought of as representing quantities that have a strength or a length and direction to them. We can think of them as a single quantity, even though they might involve a few different numbers, the components. We can use one symbol for a vector, like a bold-faced V. When you write it by hand, there are various symbols used. The first one here is probably the best one. Put an actual arrow above it. The second one here I'm about to show you is the one I most commonly use personally. A little half arrow above it. By the way, the color is just for fun, just to catch your eye. It doesn't matter what, you don't have to color them. Half arrow. Why a half arrow? Because we're a little lazy. We don't feel like writing the other part. We just do it. And I usually make it a little bit bigger than that. I usually do something like this. Something like that is the way I do it by hand. I've seen professors write the half arrow the other direction. And maybe I guess you could write a full arrow the other direction too. And some people, especially statisticians, don't write arrows above the vectors at all. They put lines below the vectors typically. Or maybe sometimes above, though that can be confusing. Yeah, probably statisticians don't do that because that would mean represent what's called a mean. So just be aware. Different people write vectors in different ways. And not just with single symbols, but also in terms of components. When writing in terms of components, say A and B, there are various conventions. In the two-dimensional case, you might write the components as this. What's that? A(I hat) plus B J hat. If you've never heard of I hat and J hat, ignore this for the moment. If you have heard of them in physics, say, maybe you know what I'm talking about here. We'll come back to it. Or maybe as a point, A comma B. Because of the natural association between points and vectors. But wait a minute, vectors are arrows, they're not really points. Maybe we should use something different. How about square brackets? Some people do that. But that could get confusing because some people think that's an interval. On the number line, closed interval. Some people write that. Pointy brackets. Though actually, if you know about something called inner products, that's trouble too. There's really no ideal way to do this. The most common ones we will use in this class are column vectors, either with square brackets around them or parentheses. And again, that's a typo there. Those lines should be showing up there. These are the most common ones we will use in this class because, especially later on, we'll be wanting to take a matrix times a vector. In the Differential Equations book, it occurs in Chapter 3. Actually, in Visual Linear Algebra Online, it occurs in Chapter 1. We'll be doing it fairly soon. Yeah, because we also often want to think of our vectors as being matrices themselves, in fact, as with one column, and we want to be able to multiply matrices when appropriate. That'll be a really useful thing. Almost done here, hang on. Well, these last few slides are still pretty important. Said vectors can be thought of as quantities. Can they be added? Yes. This is just an introduction, by the way. We are going to talk about this more in lecture 4. Geometrically, vectors are added according to the head-to-tail definition, which is equivalent to something called the parallelogram law, which I'm about to show you what these things are visually. Here's the head to tail. If I want to add V and W, where V is an arrow with this length in this direction, and W is an arrow with this length in this direction, do head to tail. In other words, put the tail of W, this spot, at the head of V. Like that. And the starting point, the original starting point for V is the starting point for V plus W. It's the tail. And the ending point of W, the head, is the head of V plus W as well. But wait a minute. If this is right, does W plus V give you the same answer? It does. If you put W here, and V here, you end up at the same point when you start at the same point. And that is the essence of the parallelogram law, which I'm going to show you in another picture here. Head to tail, V plus W gives you this pink vector, but also W plus V gives you the same pink vector. Or you can think of the entire picture as a parallelogram, and the sum, V plus W, which is the same as W plus V, it's commutative, starts here and ends at the opposite side of the parallelogram. If one of the vectors is a zero vector, then the picture is degenerate, essentially. It's just one vector with a dot at either the tail or the head. The zero vector is just a point. In terms of components, this is done, let's call it component-wise, or component by component. If V has components A, B, and W has components C, D, say, A here, B here, where A, B, C, and D are all positive in this picture, then this picture essentially visually proves that V plus W has components A plus C, B plus D. As a column vector, this equals first component A plus C, second component B plus D. And that is the sum AB plus CD. when I write the vectors in terms of components as columns. Pictures are not proofs, they just give you, they help you believe it. That's the right thing to do. But wait a minute, is this the right way to add vectors? Is this a good idea? Yeah. If you think about the physical situations, especially if you think about displacement, it makes sense to say if you travel from here to here to here, and then travel from here to here, your sum of your two displacement vectors is the overall net displacement from here down to here. Also makes sense for forces and that kind of thing, though you do need to verify that experimentally. This is our last slide, I believe. Yes, scalar multiplication. When a vector is multiplied by a positive number, also called a scalar, for a good reason, the resulting vector, the resulting arrow, points in the same direction when it's a positive number, and its length is rescaled by that number. So if I multiply a vector by 2, it points in the same direction but it has double the length. If I multiply it by 3, it points in the same direction but has triple the length of the original vector. If I multiply it by a half, it points in the same direction but has half the length. I can make drawings here, but I hope you see the idea is pretty intuitive. If I multiply by a negative number, a negative scalar, and we're calling these scalars because they rescale the vectors, you also have to point in the opposite direction. So if the vector points from here to here, like this, and I multiply it by -1, the new vector, -1 times the first vector, needs to point in the exact opposite direction and have the same length, because the opposite value of -1 is +1. If I multiply by -2, it's got to point in the opposite direction and have twice the length, because the opposite value of -2 is +2. If I multiply by -1/2, it's got to point in the opposite direction and have a length that's half the original length, because the opposite value of -1/2 is positive. If I multiply it by 0, it becomes the 0 vector. It has 0 length. Yeah. The resulting vector is the 0 vector. Bold-faced 0. In terms of components, scalar multiplication is also done component-wise. If I take a scalar, a number, call it, say, lambda. It's going to be a common letter we use for scalars, numbers, times the vector whose components are a, b, say. I do it component-wise. The new vector has components lambda a times lambda b. That's what it means to be done component-wise. When I added the vectors on the screen here, it was done components. I added the first components and I added the second components. Combining vector addition and scalar multiplication also allows us to define vector subtraction and give it a geometric interpretation. That is the end of lecture 3B. I would encourage you to take the time to think about that. Let me give you another hint. V minus W should be thought of as V plus -1 times W. That's how you can use vector addition and scalar multiplication to define what vector subtraction should mean. Now, you try to figure out some pictures how to give that geometric meaning. That's definitely a very good exercise. Okay? And thanks for watching.